Okay, so section 11.5 is going to talk about alternating series. And what I want to do is start out with a bunch of different sequences. The first one is -1 to the nth power. Now starting at n equal 1, then n equal 2, n equal 3, 4, etc. What you can see is that the even powers are going to be positive, the odd powers are going to be negative. Let's switch up to b sub n and look at the sequence dictated by that. Now the difference here is that when you plug in an n equal 1, you'll get to the 0 power, so that'll make this -1 to the 0 power a +1. And then it'll alternate from there. So by changing this from n to n-1, it's just simply going to change the pattern there. So it alternates starting with a positive number and then a negative number. How about c sub n, -1 to the n plus 1? What's that going to look like? What's the first term going to be?
Positive.
Yeah, it's going to start out positive. So effectively, it's the same as b sub n, right? I mean, those two work out to be the same. So that's okay. It's just something to keep track of, or something to note, is that these two are the same. So it doesn't matter if you have n-1 or n plus 1. And last but not least, cosine n pi. When n equals 1, you're looking at the cosine of pi. What's the cosine of pi?
1.
Try again. Yeah.
Oh, sorry, -1, sorry.
There we go, -1. And then 2 pi, you're back at the origin, and so on. So again, you know, you've got all these terms that alternate. This one starts with a negative. That's okay, you know. But basically, what I'm trying to get at is that with terms like this as part of a series, you can get things to alternate. And alternating series are kind of special. They're going to have different properties that allow us to find their sum, or at least estimate their sum. So let's write this. Alternating series. So you're going to have the sum from n equals 1 to infinity of a sub n is really going to be composed of a couple parts. You're going to have some part that makes the series alternate, like -1 to the n-1, and then whatever other term is. So basically here, b sub n is the absolute value of a sub n. All right, so you got the part that alternates, and then the other stuff. So b sub n is just the absolute value of this term. Now, this is going to converge in a couple, or with a couple easy conditions. This converges if it's a decreasing sequence, that is b sub n plus 1 is greater than or equal to b sub n, and the limit of n approaches infinity of b sub n equals 0. So basically, if it's a decreasing sequence with a limit of 0, then it's going to converge. And that's nice. Basically, it's your alternating series test. Is the test for convergence, decreasing, and the limit of 0. Now, there's one other thing that is handy here, and that is your remainder. R sub n is going to be S, which is your true sum, minus S sub n, which is the sum of the first n terms, or the first partial sum. So this, you can call it the remainder. Is going to be less than or equal to b sub n plus 1. What's b sub n or b sub n plus 1. Basically, it's the first omitted term. So first term omitted. So that's kind of nice. It gives you a quick way to decide if, or decide the rough size of the remainder or your approximation. But just by looking at the size of the first term you left off. That's actually really handy, and we're going to take advantage of that later in this chapter. For now, let's take a look at some examples. And call this one example A. 3/4 minus 3/6 plus 3/8 minus etc. What would be the next term, just out of curiosity?
Tenths.
Which one?
Negative 3/10.
Yeah, thank you. Negative 3/10. And let's squeeze it in here. Why not? Negative 3/10. All right, so this is a series. And another thing that we can notice about it is that it's an alternating series. So what we have to establish is, are these terms decreasing? And what's the limit of these terms as that approaches 0? So I guess the first thing we would need to know is, what's b sub n? B sub n is going to be the general form of these terms. So, all right, that's, this is a sub 1, a sub 2, a sub 3, a sub 4. Now, I'm not worried about the alternating part. We can use one of those series or sequences up above to make things alternate. But I want the general form of these things. Well, the general form is going to have a numerator of 3. Well, what about the denominator? Well, a sub 1 is a sub 1 is 4, a sub 2 is 6, and then 8, and then 10. One thing that can catch your eye is that these are all even numbers. Now, even numbers can be generated by 2 times n. But does 2n, would that match all the things I have going on here? Not quite, because 2 times 1 would be 2. I got a 4 here. 2 times 2 is 4, and I got a 6 here. So I'm pretty close. Can anyone figure out a way to finish this off, though? What else do I got to include so this denominator would match these things?
Could add 2.
Yeah, add 2. And check it out. A sub 3, 3 times 2 is 6, plus 2 is 8. Perfect. So that's our general term. Now that we have that, we can check out a couple things. We want to check that they're decreasing and that their limit is 0. So let me rewrite that here. B sub n is 3 over 2n plus 2. And just for giggles, let's practice doing something that we're going to have to look at later when we work with the root test and the ratio test. Actually, just the ratio test. Let's take a look at b sub n plus 1. So really what you're doing is you're plugging in an n plus 1 here. And if you simplify that, that's going to be 3 over 2n plus 4. 2n plus 4 is going to be bigger than 2n plus 2. But when you divide 3 by a bigger number, this will be less than this. So b sub n is greater than b sub n plus 1. These terms are decreasing monotonically. Now, you don't need them to decrease monotonically in order for this to work, but that's one condition we needed here. This is one condition we needed to show that the series converges. The other one is we want to take a look at the limit. Limit as n approaches infinity of b sub n of 3 over 2n plus 2. L'Hopital's rule wouldn't be appropriate here, and it's overkill anyways, but that limit is 0. So if the limit is 0 and the terms are decreasing in an alternating series, the series converges by the alternating series test. And we'll just conveniently abbreviate that as the AST. All right, how's that first one look? Doing okay on that one?
So if it didn't if it didn't meet our requirements, would we not know anything about it, or would it diverge?
I guess it could do either of those. Might have to use a different test, but if the limit didn't go to 0, then it would diverge. Well, let's see. Would diverge necessarily? Yeah, I guess I'd have to think about that one. If the limit's not going to 0, then it's not clear what's going on with this thing. Yeah, you have to think a little bit more carefully on this one if the limit didn't go to 0. Yeah, it's a good question. Trying to think if necessarily means that they diverge or not. I can't say yes or no, because what I'm thinking of is like telescoping series that collapse, and the terms might not actually go to 0, but yeah. No, I guess in a telescoping series the terms do go to 0. It's just that they're collapsing on themselves. I don't want to say something and be wrong. So yeah, if the terms don't, if your series doesn't match these conditions, then you're just gonna have to use a different test. Yeah, so it's a good question, and I'm sorry I can't give you a more definitive answer on that one. Anything else that I can dodge or avoid here? Okay. Let's take a look at another example, kind of like that. First one. So this time we're going to have a series that looks like this. -2 over 3 plus 4 over 4 minus 6 over 5 plus 8 over 6 minus 10 over 7, etc. Now, what I find useful in problems like this, when I have to come up with the series itself and the general form, is to write, stuff like this underneath. So that way I can try and line things up. So for instance, if I'm trying to figure out what b sub n looks like, and that's just the absolute value of whatever general term is coming up with this, I know I have a fraction, and we'll look at the terms in the numerator. Now, we're not worried about the alternating stuff. Look at the 2, the 4, the 6, the 8. Can you think of the general pattern that's going on to give me the terms in the numerator?
2n.
2n. Thanks, Michael. 2n. Someone else for the denominator, please. What's going on with the denominator? I have a 1 here and a 3 and a 2 and a 4. I mean, are these random in the denominator?
N plus 2.
N plus 2. Thank you. So 2n and n plus 2. Nice. So with that, now that I got this, I can actually rewrite this series as maybe the sum from n equals 1 to infinity of -1 to the n, 2n over n plus 2. So there's my alternating series. The question is, does it converge? Well, that's a good question. There's two things we have to look at, and I think it fails both of them. We have to look and see if the terms are decreasing and if their limit is going to 0. For me, the second one looks pretty easy, so let's go with that one. Limit as n approaches infinity of b sub n. Well, let's give me the limit as n approaches infinity of 2n over n plus 2. So we could use L'Hopital's rule here if you really wanted to, but that's like squirrel hunting with a bazooka. So instead, let's just notice that the degree of the numerator and the degree of the denominator match. So the limit is just a ratio of the leading coefficients. And since that ratio is different than 0, the series diverges. Yeah, has to go to 0. All right. Not bad. Not bad. Let's do some more examples like this kind of stuff. Any questions on B before I move on to our next example? Looking good there. All right. So let's take a look at the sum from n equals 1 to infinity of 5 times -1 to the n times e to the negative n. There's probably a couple things that I would do with this series, working on it for myself. Does 5 depend on the n in any way?
No.
No. So I can factor that out. It's just like having a constant of 5 that's part of a bunch of terms. You can factor out a greatest common factor. So I'll factor out the 5. And then because this has a negative exponent, I'm going to get rid of that and put it in the denominator. -1 to the n over e to the n, like that. There's really a couple of things that we can do on this one. But this is an alternating series. It starts out negative, that's okay. Doesn't matter if it starts out negative or positive. If you look at b sub n as 1 over e to the n, that's going to be greater than b sub n plus 1, which is 1 over e to the n plus 1. Has a bigger exponent, so the denominator is bigger. This one is bigger than this one. So that's one thing we got to check. Second thing we got to check is the limit as n approaches infinity of b sub n. What's that limit going to be?
0.
0. And I think I've used this enough that hopefully you're getting used to it. Therefore, the series converges by the AST.
Wait, how did you know that 1 over e to the n is greater than 1 over e to the n plus 1?
Because I've got an extra term of e here in the denominator, so it's e times e to the n. So since e is like 2.7 or something like that, when I multiply e times e to the n plus, or e times e to the n, I'm going to get a bigger number, right? So if I got a bigger number, I've got a bigger denominator.
Oh, okay, I see.
And dividing 1 by that bigger denominator gives me a smaller quotient.
Right. Okay.
You know, you bring up a good little question here. Just let me remind you, and it's funny, I was teaching Calc 2 years ago at the same time I was teaching beginning algebra, not even beginning algebra, pre-algebra. It's the lowest course I teach. And there was two little topics that actually blended well together from one to the next. It was funny. But if you have A over B and want to show it's is greater than B over C, or C over D, so if this is true, then the cross products have to be in that same proportion. So it's going to be A times D has to be greater than B times C. So what would that look like for us? So that would be 1 over e to the n is greater than 1 over e to the n plus 1. If I cross multiplied, I get e to the n plus 1 is greater than e to the n. And that makes sense because this is really e times e to the n. So yeah, that fits. So it's a nice way to look at two things and show that, okay, one of them is actually bigger than the other one. Because you had a really good question. It's like, well, how do I know that the one's that really that big? You can always look at this kind of proportion approach and cross multiply. Does that help out a little bit more?
Yeah.
All right, thank you. We're on example D now. So let's see. Sum from n equals 1 to infinity, -1 to the n, 5 times n to the n over n factorial. Now this one's kind of wild. N to the n. Wow. That's pretty wild. And then you got factorial. In computer science, sometimes they call this the bang. And in other places you'll find them called the bang as well. But let's take a look at B sub n in this case. B sub n is going to be 5 n to the n over n factorial. Now, do you remember the deal with n factorial? What's that represent? Represents
5 times 4 times 3 times 2 times, or no,
yeah.
wait, yeah,
Well,
sure, sorry.
Yeah, no, yeah, exactly. We're just going to apply that to n here. So it's going to be 1 times 2 times 3 times all the way up to n. Now in the numerator, I've got the 5, which I kind of want to squeeze out in front here. So there's my 5. And then n to the n is n times n times n, n times, right? I mean, that's what n to the nth power is. It's n multiplied by itself n times. Now, some of this will cancel, you know, and this next term is an n and an n minus 1, and that kind of almost cancels. But what you can say for sure is because n is greater than 2 or n is greater than 3, is that whatever this cancels out to, this is greater than 5n. You're just looking at these terms. If you suppose that every one of these terms canceled out, saying, all right, that's close enough, this is still greater than 5n. And why is that an important observation? Well, remember, there's two things we got to test. We got to test if b sub n is greater than b sub n plus 1. What's the second thing we got to test? Limit as n approaches infinity of b sub n. What I'd like is I'd like to see that equal to 0. Is that going to happen here? What's the limit as n approaches infinity of b sub n? Some help out on there in this one. What's that limit?
Infinity?
Yeah, infinity. So does that series converge?
No.
No.
No, it diverges. So therefore, series diverges. Okay, done. That's all we got to worry about on that one.
Mr. Parent,
Yes.
I'm still confused on how you're coming to the conclusion that b sub n is greater than b sub n plus 1. I know you just explained it, but
Oh no, I didn't actually mean to imply that this is true. This is what we got to check, right? And in fact, it wouldn't hold true in this case. B sub n would actually be less than b sub n 1 plus 1. These terms are going to be increasing. So it fails this. So it fails that, and it fails this. It's not going to have a limit of 0. So yeah, good question. I didn't mean to imply that this is true. I just meant to say these are the two things we got to check. And if it fails either of them, it's going to fail the AST.
Professor,
Thank
if we're ever unsure about the first rule, can we just use like plug-in values for n and test it that way to confirm?
Sometimes, but I mean, sometimes that could lead you astray. If you're going to try that, I would pick some large values, because sometimes what happens is that a series could kind of go up and down a little bit. It could, you know, decrease for a while and then start increasing. So if you catch it on a decrease, it might lead you astray. But if you pick a number large enough, you know, then out here you should be able to see if it's decreasing or increasing at that point. It's not a bad thing to do, because in my mind, I think what really has to go on when you're doing these kinds of problems is you have to have an intuitive sense if you know if it converges or diverges first. You should be able to look at that and say, you know, I think it converges or diverges. And let me repeat something that I shared with you the other day. We'll call it the pecking order. Who's first? Who gets first? Now, what the pecking order here I'm going to list is going to be how fast do these terms grow. there's the log of n is going to be less than a square root of n, is going to be less than a polynomial term of n, is going to be less than a factorial of n, is going to be less than n to the n. So with these kind of in mind, that general order, you might look at that and say, oh, well, I've got this in the numerator bigger than something in the denominator. So the bigger over the smaller, this is going to get bigger with larger values of n. Now this is kind of also getting to my point. Now let's see. Now, my earlier point was that you want to check larger values of n. This one I think is just going to increase from the get-go. But sometimes those terms do, like I said, that they'll decrease for a while and then they'll increase. Anyways, looking at this, I'm like, okay, that's going to get really big faster than this is going to get big. So this is going to go to infinity. It's not going to go to 0. But yeah, keep in mind that general pecking order. I think that helps out. Gives you an intuitive sense of what to expect. You know, I should work in there. Let's see, I guess I got a power. Oh yeah, there is one more term I guess I can squeeze in right there. And that would be a to the n. You know, assuming that a is greater than 1. Yeah, so your kind of your geometric series.
Thank you. That helped.
Yep. Okay. Yes.
Why did you replace, like on the bottom there when you did the limit, why did you replace b sub n with 5n?
Oh, because whatever this is, I mean, I can't really easily simplify this because I don't know what n is, but whatever it is, it's bigger than 5n, and it's enough to say, all right, well, if this is bigger than 5n and 5n is going to infinity, then this has to go to infinity. Okay. So that's what I did. It was just a cheap workaround defining the limit of this as n approaches infinity. Because especially with that factorial in the denominator, it gets a little messy. So, yeah. So I hope that answers that.
Yeah.
All right. Cool. Well, thank you for those questions. Let's look at, I don't know, another example. Except this time I'm going to have you work it. So it's going to be example E. Sum from n equals 1 to infinity of -1 to the n minus 1 times b sub n. And our series is going to look like this. So it's up to you to figure out the nature of b sub n and prove that this thing converges or diverges. So let me correct a quick little thing here from our alternating series test. This should be b sub n is greater than or equal to b sub n plus 1. And then the limit is b sub, or as n approaches infinity of b sub n equals 0. So those are the two things we want to check. And we'll check those first. But I guess all that relies on us determining what the form of b sub n is. So then we get b sub n.
1 over the square root of n plus 4.
Perfect. 1 over the square root of n plus 4. Again, kind of like what we did earlier, you can write out n equals 1, n equals 2, n equals 3. And, you know, eventually start seeing, okay, this is consistently 4 more than my value of n. So that gives you your b sub n. So as far as b sub n is going to be 1 over the square root of n plus 4. And that's going to be greater than b sub n plus 1, which is going to be 1 over the square root of n plus 5. And I didn't put in n plus 1 plus 4. I just summarized it as n plus 5. So we got the first condition. The second condition, limit as n approaches infinity of 1 over the square root of n plus 4 is 0. So it converges by the alternating series test, which is perfect. That's what we wanted. Converges. Retire U by the AST. All right, I think we should probably try and switch it up a little bit. Let's work with our remainder stuff, because the remainder stuff is really cool and powerful. I really like the remainder theorem here. So before I do, are we doing okay on question E? All right. Let's see. So wrong example. F then. Let me remind you that the remainder after n terms is going to be s minus s sub n, and that's going to be less than or equal to b sub n plus 1. So this is the true sum of your series. That's the sum of the first n terms. The remainder is the difference between your true value and your approximation, and that's going to be less than the first term you leave off. So you could get a problem like this. N equals 1 to infinity, negative 1 to the n minus 1 times n squared over 10 to the n. Okay, so let's see. I want to approximate this to 4 decimal places. Approximate to 4 decimal places. That means we want to find where the error is less than 0.0001. So R sub n is less than 0.0001. Okay, so if we do that, then we should be in good shape. Now there's two approaches here. One is you could solve this inequality. Although to be honest, I'm not sure how you do it. We want to find out at what point, you know, the term that you leave off for what value of n, is this inequality true? The second approach is to guess with the table function. And that's what I'm going to be recommending, is that we just guess using our table function. So let's do that. Take out your graphing calculators. And let's get them warmed up.
So we're given the 0.001, correct?
One more time.
We're given the 0.001.
Sort of. They say 4 decimal places. So that means you want your error to be less than 1/10,000th. That's essentially what it's going to mean. So yeah, you have to be given that much.
Thank you.
Mm-hmm. Okay, so let's go over to our y equal. You know what? Let me just check the mode here real quick. Yeah, mine's still in sequential mode. That's okay. When I hit y equals, I'll clear this stuff out from the other day. And I'll clear this out as well. Just don't want to cloud up our answers. And let me type in b sub n, which would be n squared divided by 10 to the n. If you want to get fancy, you can do second and then log 10 to the n like that. Great. And now what I'm going to do is I'm just going to plug in values of n until I find something that gives me a small enough number for my remainder. So second table, uh-oh, oh my, it's not liking something here. Table,
Maybe your window.
Yeah, that's what I was thinking. Let's just do 5 maybe. Second table. Still, that shouldn't be happening. Let me take a look back at go to. That doesn't make sense. I get an overflow here.
It works for me, but my n of 0 does throw an error in the table, but then it proceeds to list it out.
Yeah?
Yeah.
Yeah, mine worked fine too.
That's frustrating. Let me do n2 as 2. Overflow. Now, overflow should only happen if I have like 10 to the 99th or bigger. Actually, bigger than 10 to the 99th. I'm not sure I see where that's coming from. All right, tell you what, let me change my mode here. I guess I got to quit this first. So quit mode.
Maybe you already have like values in your table.
I'm thinking that might be part of the problem, but
And it's like some of them may be too big.
yeah, it could be, but it feels circular. Like I can't get rid of the values until I see my table. Yeah. All right. So yeah, this is what's going on. It's exactly what you're saying. I had values in my table. So let me delete those. Wow. How about that? I learned something new today. How cool. And now we'll go back and try it again. So n squared divided by 10 to the n. All right. Now just for a little quick FYI, reminder, when values on your table get small, they're probably going to be presented in scientific notation. So for instance, 0.00054 would be written in scientific notation as 5.4 times 10 to the negative third. But what you'll see on your calculator is 5.4 e negative 3. So what you're going to have to get used to is reading this and saying, okay, well, there's really 3 decimals in front of that place. And we're looking to get essentially like 5 decimals, really. Something less than that, which is going to be putting us into the 4 zeros. So I might have said 5. I think 4 would be where we want to be. So let's just plug in some numbers. I'm going to start with 5. Is that working? So 2.5 times 10 to the negative 4th. Let's just write that out. So at n equal 5, we've got 2.5 times 10 to the negative 4th So it's going to be 0.000 25. All right, so it's not quite enough, right? Because it's got 3 leading zeros. We need 4 leading zeros. So let's try another one. Let's try n equals 6. So that's going to be at n equals 6, we have 3.6 times 10 to the negative 5th, 0.000036. Again, not small. And well, let's see, is it small enough? Yeah, actually, it does seem small enough, doesn't it? That's going to be less than 0.0001. So any error that we make is going to be less than 1/10,000. So you're going to have 4 digits of accuracy. So if we sum up the first 5 terms in the series, the 6th term is the first one that's left off, meaning our error is going to be smaller than this. So sum up n equals 5 terms like that. Now, we're not quite done there. Let's see, 5, 4 decimal places of accuracy. Seems right. Seems right so far. Now, the big question is, you know, how do you sum up those first 5 terms in this series? So that can be a little bit of a pain. So let's work on that. S sub 5 would be the sum from n equals 1 to 5 of negative 1 to the n minus 1 times n squared over 10 to the n. I wouldn't want to do that one by hand. Would you? And be, let's see, at n equal 1, you have 1/10. At n equal 2, the minus 2 squared is 4 over 100 minus to be plus 9 over 1,000. I guess doing it by hand is not that bad. Next one would be what, 16 over 10,000, and then 25 over 100,000. There. So in a pinch, you could do it by hand. Is anyone interested in seeing how to do it with a little technology? I think we've gone through this before, but I'll be happy to show you again. Or you want to do it by hand? It's up to you.
Can you show us by the technology again?
Okay, sure, sure. All right, so let me exit out of here. Clear this out so you can kind of follow along my keystrokes if you need to. Let's start by going to the list menu, second, and then stat. And go over to ops, and then go over to math. I first want the sum, so that's the 5th option down. And then I need a list. I want to sum up the list of those terms. So I want to sum up these 5 terms, and I'm going to give my calculator to generate that for me. So back to our list command, second and list. This time go over to ops. And we want sequence, the 5th term down. So just type a 5, or you can cursor down and press enter. Let's enter on our expression. There's going to be negative 1 raised to the parentheses n minus 1. You need the parentheses there. Followed by an n squared divided by 10 to the nth power. So negative 1 to the n minus 1 in parentheses times n squared divided by 10 to the nth power. Our variable is going to be n. That's already set. Starts at 1. This time it's going to go up to 5. Step of 1, and then paste. And that should paste in the command into the home screen of my calculator. And at the beginning of this, I had the sum. So let's just put a right parenthesis at the end, close things off. And bam, there you go. So that's the sum of the first 5 terms. And that should be accurate. This should be an accurate representation of the series to the 4th decimal digit. So 1, 2, 3, 4. And it looks like that rounds to a 7. So about 0.0677. I'm a little bit bothered by that because in my notes I had 0.0676. And I think I used an extra term in my notes, but I'm not seeing any mistake there. So, let's just add in one more term here. So if I hit second and then enter, and I go back and make this 6, is that going to change things? I bet you it's going to change it by just the 1 digit. It does. All right.
When you're choosing S sub n, like, can you just choose like any number, or does it?
Well, no, you don't want to just choose any number. So what we want to do is we want to go far enough out in this series that the first term we're leaving off is less than our required error. Because remember, R sub n, the remainder, we want that to be less than 1/10,000th. Problem is, and n equals 6, that was less than 1/10,000th. Unless I missed something. Oh, crap. All right, wonderful. I must not have started the recording there. And now I'm recording some file